The other specific type of motion that we look at in extension 1 is simple harmonic motion. So let's define it. Basically, it's very, well, as the name suggests, it's very simple motion. It just goes backwards and forwards between 2 points in a symmetric sort of way. So at any instant, its acceleration is directly proportional to its displacement. Okay. It's directly proportional. It does have to be in the opposite direction, however, otherwise it wouldn't stop. Once we're in the positive displacement, so I'm over here in the positive displacement, and I'm moving with a positive velocity, but my acceleration is negative, so I'm slowing down, I'll eventually stop. So, but the acceleration is still negative, so I'm going to start moving backwards. So now I'm moving in the negative direction. I'm going to be getting quicker and quicker and quicker because acceleration is until I hit 0. And then as soon as I move into the negative displacement, now my acceleration is positive. And so I'll be slowing down till a point where I stop, and then I'll start pulling me back. But now I'm going to be speeding up, hit the origin, slowing down, hit the end point, turn around, speeding up. And it just keeps going backwards and forwards and does that. So we start with acceleration is proportional to displacement, which means it must be equal to some constant times displacement. But rather than have k, because it has to be in the opposite direction, to ensure that constant is negative, we make it negative n squared. And that way I know the constant will always be a negative number. All right, so that's basically it. There's simple harmonic motion. That's all we really know about it. But fortunately with calculus, we can now go and derive other things. So acceleration is in terms of displacement. And so as we saw yesterday, that means it could be written as d dx of a half v squared. So if I want to come up with a velocity equation, then we integrate both sides. And so half v squared will equal minus a half n squared x squared plus a constant. So multiply everything by 2. Notice I didn't bother saying 2 times a constant, because 2 times a constant is still a constant number. Some initial conditions. Well, we didn't have any. So let's just assume I'm going to start out at that endpoint. And so out of that endpoint, we said, remember that's where we stopped, and I'm going to start coming back. So I know out at the endpoint the velocity will always be 0. So whilst they didn't tell me in the question, because it's simple harmonic motion, I know that has to happen because I'm going backwards and forwards between the 2 points. So if I'm going to stop it at A, its velocity must be 0 there. And I've just called it A because the amplitude of the motion, if you like. So subbing that in, the constant becomes n squared A squared. And so velocity squared is minus n squared x squared plus n squared A squared. Factorise the n squared. So it's at any particular point then, velocity will be plus or minus, depending on whether we're going to the left or we're coming back. And it'll be n times the square root of a squared minus x squared. Okay, some things to note. Mentioned this yesterday. Well, velocity squared, or in other words, whatever's under the square root sign, will always be greater than or equal to 0. And this proves what I was talking about, the particle moving between the 2 points. So if I solve this inequality, I in fact get that x is in between minus a and a. So I said I'm going to stop out at a, but now we've just proven that the other end, it also stops a units from the origin as well. So the path is always going between minus a and a, assuming, of course, the centre of our motion is the origin. All right, well, let's try and work out a displacement equation. So velocity is dx dt. Now I've got to choose whether to take plus or minus. The initial condition was velocity equals 0. So plus or minus, it doesn't really matter, because plus or minus 0 is 0. I've chosen minus 0. So if our initial condition, we're out at the amplitude, I'm going to choose the negative. The reason being is I'm going to end up integrating. And if I've got minus the integral, and you'll see it in a sec, I can go straight to inverse cos. If it's at the origin, I'm going to choose the positive. And then when I integrate, I'll end up with inverse sine. So here we go. We'll turn it upside down, and now you might be seeing the inverse cos function, or the derivative of it. There it is, minus 1 on the square root of a squared minus x squared, or also times n. So if I integrate both sides, I'll get 1 on n. The integral, we're starting at a, going to some general displacement of x. That is just our straight inverse cos. So we'll get inverse cos of x on a. Sub in x, sub in a, and we come up with inverse cos of 1. Inverse cos of 1 is 0. That's why I've chosen the negative. So that bit comes out nice. Turns out to be 0. So 1 on n, inverse cos x on a. Well, we want to make x the subject of that. So once I play around with it, you'll see I end up with a cosine function. Simple harmonic motion is basically a trig function, sine or cosine curve. Now I can explain a bit better why I chose negative and wanted to go inverse cos. Think about your graph. The cosine graph starts at the amplitude. So if the initial conditions they're telling me is this motion starts at the amplitude, I want a cosine function. It's going to make life a bit easier because straight away it'll match the motion. Whereas if it starts at x equals 0, then a sine curve does that. So I'd prefer to have the sine curve when I integrate. So all right, what can we quote? What can we use? We know acceleration is minus n squared x. We can quote that. V squared equals n squared a squared minus x squared. Can't really quote it. However, if it's one of those questions where might only be worth a mark, then yeah, it's acceptable. They'll allow you to do that. It allows us to find the path of the particle. That's one of the useful things that's there for. We then know x is a cos nt, or sine, depending on which problem we have, whether we're starting at the origin or we're starting at the amplitude. What they'll tend to happen is sometimes we'll start with acceleration and they'll want us to get to displacement. Sometimes they'll start with the displacement and head to acceleration. Now, we'll look at some examples in a sec. All right, period, 2 pi on n, it's a cosine function or a sine function. That's the period of a trig function. But we now have this new thing called frequency. And frequency is simply the reciprocal of period. So 1 over the period. Now, period is the time for one complete oscillation. So go backwards and forwards. We've done the whole path, well, twice in a way, because we've gone backwards and forwards. That's the time. Whereas frequency is the number of oscillations per time period. So how many oscillations could I do in a second or in a minute, whatever the time units are. All right, so this one is starting with the displacement equation. It's telling us it's 4 sine 3t. One of the most common questions they will ask is, show that it's moving in simple harmonic motion. Now, if we start with the displacement, all we have to do is show that acceleration is equal to minus some negative constant times displacement. So I just differentiate twice. Differentiate twice, I get minus 36 sine 3t. Well, displacement was 4 sine 3t. So indeed, I have minus 9 times x. I have a negative constant times displacement. And that's enough. That's all we have to do to prove it moves in simple harmonic motion. Because that is the fact we know about simple harmonic motion. If we can show acceleration is equal to a negative constant times displacement, that must be simple harmonic motion. Okay. Now, if it's not, this is centered at the origin, of course. If it was shifted, then you would show it's some multiple outside of x minus whatever the shift is. That would be equivalent of doing that. It did say, find the period, did it? Yes, it is. Period of motion, 2 pi on 3. So, assuming it's seconds, didn't actually say, but 2 pi on 3 seconds. Find the interval in which the particle moves. Now, I've got x equals 4 sine 3t. It's a trig function. I can just write this answer down. I don't have to worry about that v squared equals n squared, a squared minus x squared. I've got it right there. X is 4 sine 3t. Where does x move in between? Not a trick question. 4 and minus 4. So there you go. I can write it down straight away. What's its greatest speed? Well, velocity is 12 cos 3t. What's the biggest that function's ever going to be? 12. There you go. We've got our answer. So I don't have to actually use, well, I did use calculus because I've differentiated those terms, but it's more our knowledge of trig functions which allows us to solve the problem and can solve it very quickly. All right, this time we got the other way. They've given us that acceleration is minus 4x, and they've given us some initial conditions. We're starting 3 centimetres to the right, travelling with a velocity at 6 centimetres. So this is telling me I'm not actually starting at either the centre or starting at the end point, because I'm 3 centimetres to the right. I know there's no shift happening because its acceleration equals minus 4x, so it is centred at the origin. And I've got a velocity at this point, so I can't be at the end point. Find the interval in which the particle moves. So this is going to have a little bit more working to do. Well, acceleration is minus 4x, so d dx of a half v squared is minus 4x. Integrate, and we'll end up with our v squared formula. Something that links displacement and velocity. They told us x equals 3, v equals 6, the constant is 72. I now have the expression for v squared. I can go and find the path of my particle, because v squared, of course, has to be greater than or equal to 0. So in this case, our particle is going between 3 root 2 minus 3 root 2, travel in between those two. They asked us some more. Find the interval and determine the greatest acceleration. Okay, acceleration is minus 4 times the displacement. The greatest acceleration would have to happen at the greatest displacement. So I just sub in the endpoint now to acceleration, and I get my greatest acceleration, 12 root 2. So 12 root 2. So have a look. There's our path. We're going to have endpoints in the centre of motion. Things that are going to happen. Out at our amplitudes, that's where we stop. So velocity must always equal 0. That is where acceleration will be a maximum. And one spot will be in the negative direction, one in the positive direction. But that'll give us our maximum amount. At the centre, that's where velocity, although I hate using the term velocity as a maximum, I think I prefer to say that's where speed is a maximum, because there's that never-ending problem about, is a negative velocity slower than a positive velocity? So hopefully they would actually ask, when is speed a maximum? But it's still going to be at the same point anyway. It's just what the value is becomes the debate. Okay, so there we go. 3D, they're the ones that start with the trig, and 3F are the ones that start with the acceleration.